Designing a shipboard suitable tactical aircraft is one of the most underestimated endeavors in our industry, and many a design team has discovered that truth the hard way. Over the next few minutes, you'll become acquainted with some of the more critical issues which must be considered in developing the maritime variants of the Joint Strike Fighter family of aircraft. First and foremost, ship-based aircraft must have the structural integrity to withstand the severe loads incurred during launch and recovery. For launch, the Navy variant must be configured with a launch bar and holdback fitting compatible with the carrier's catapult launch system. During the 300-foot catstroke, a tow force of up to 240,000 pounds is applied to the aircraft through the launch bar. Acceleration of up to 6 Gs can be experienced. A shipboard arrested landing, or trap, requires the aircraft to be equipped with the familiar tailhook, but also with high-strength landing gear and a keel structure able to safely absorb and distribute landing loads. Aircraft routinely touch down with sink rates of up to 15 feet per second and decelerate from their approach speed to a complete stop in 340 feet. These loads can be quite severe, especially during off-center and in-flight arrestments. The short takeoff and vertical landing variant is by no means immune to high launch and recovery loads. Its structure must withstand the centripetal forces during launch caused by the curvature of the ski jump ramp, and it still must land on a pitching, rolling flight deck. Ask any naval aviator, and you'll learn that shipboard landings are one of the most demanding tasks at sea. The acceptable touchdown area, effectively just 120 feet long by 30 feet wide, leaves little margin for error, especially with personnel, aircraft, and other equipment routinely positioned in close proximity. The aircraft must possess good flying qualities for safe completion of the landing task. Good takeoff flying qualities are required for catapult launch, as well as short takeoffs. No unusual control inputs should be required of the pilot, and the rotation after launch should be prompt to minimize settle off the bow. Another consideration for shipboard suitability is the aircraft's ease of handling on the deck. This includes geometric compatibility with all obstacles in and around the flight and hangar decks, size and weight compatibility with shipboard elevators, and compatibility with standard tow tractors and spotting docks. Precise steering control is required for maneuverability around the flight deck, especially when taxiing into the catapult shuttle. Spot factor, which quantifies an aircraft's flexibility in deck positioning, is closely monitored during the design. Shipboard operations introduce many unique maintenance and supportability considerations, primarily due to the harsh sea environment and the limited space available for maintenance actions. Ship motion requires aircraft to be equipped with multiple tie-down points, while the salt-filled air requires all components to be corrosion resistant. Since aircraft are routinely parked in a tail-over-water spot, locating critical aircraft components forward of the main mounts is highly desirable. Likewise, engine removal must occur within the shadow of the aircraft. Furthermore, ship-based aircraft must be compatible with all current ship support systems, as well as ground support equipment or yellow gear. During shipboard operations, the JSF will encounter a particularly severe electromagnetic environment. A wide array of high-power transmitters operate in close proximity to aircraft operations. As a result, all aircraft electrical components, especially engine and flight controls, must be made robust to electromagnetic interference. Lastly, the environmental impact of JSF aircraft operations in the shipboard environment is of considerable concern. The JSF's powerful engine will yield noise, heat, and jet blast footprints that are likely to exceed those of existing aircraft. Since space constraints prevent greater separation distances, the effectiveness of the protective gear worn by flight deck personnel needs to be monitored closely, as do the effects on the ship's structure and neighboring aircraft. Shipboard compatibility can be achieved only through diligent attention to detail in many critical areas. The Joint Strike Fighter program has established a carrier suitability integrated product team to draw focus on these critical areas and to ensure the JSF maritime variants will be compatible with the ship platforms from which they're designed to operate.
At Edwards Air Force Base, the Navy X-35 was flown to the Patuxent River Flight Test Center for extensive sea-level carrier suitability tests. While similar to the U.S. Air Force and Marine Corps X-35, the Navy X-35 has special characteristics designed to meet the demanding requirements of carrier operations. These include a larger wing and control surfaces, the addition of ailerons, and special structures to absorb high-impact landings.
The handling qualities are superb throughout the flight envelope we tested, and in fact, the handling qualities of the X-35C, our Navy airplane, make it ready to take to the ship now.
The Navy variant prototypes the first carrier-supportable, low-observable aircraft, which will provide the Navy with breakthrough, all-weather, precision strike capability. While at the Patuxent River Test Facility, the Navy X-35C was flown by both Navy and Marine Corps pilots. Early in 2001, the CTOL X-35A was converted to the STOVL X-35B. The aircraft was fitted with a shaft-driven lift fan propulsion system, which includes a vectoring rear nozzle, wing-mounted roll post ducts, and a counter-rotating lift fan manufactured by Rolls-Royce and driven by a Pratt & Whitney F119 611 engine via the drive shaft. The fan's cool thrust multiplies the engine's lifting force and creates a more benign ground environment, a critical factor in both shipboard and land-based operations. STOVL flight testing of the Marine Corps, Royal Air Force, and Royal Navy X-35B began on June 23, 2001, with a series of vertical takeoffs, hovers, and vertical landings. The shaft-driven lift fan system fulfilled its promise of delivering reliable performance and tremendous lifting force, even in the unfavorable conditions of the high, hot California desert. Testing then progressed to short takeoffs, aerial refueling, in-flight conversion between STOVL and CTOL propulsion modes, transitions to hover, and vertical landings. On July 20th, 2001, the X-35B STOVL variant became the first aircraft in history to achieve a short takeoff, a leveled supersonic dash, and a vertical landing, all in a single flight. When testing concluded 2 weeks later, the aircraft had completed 17 vertical takeoffs, 14 short takeoffs, 27 vertical landings, and 5 supersonic flights, and was flown by 4 different pilots. Throughout its STOVL flight test program, the X-35B required no modifications or changes. By the end of flight testing, The 3 Lockheed Martin JSF demonstrators had met or exceeded all government requirements and all company objectives.
The fact that our measured performance
show us the Navy and Marine Corps' newest enlistee, the F-18 Hornet.
It gives me great pleasure to present to you the F/A-18 Super Hornet.